All right, with the population proportion, we estimate from the sample, we find the variance of the proportion, and then we construct the confidence interval for the proportion estimate. Now it comes to the last session when we are trying to estimate the population proportion. What is the sample size that we need to collect? Similar to the y-bar estimate, we set our bounds of error and also the significant levels. Okay, in other words, we try to find that the probability of the errors, which is the estimate to the true value, greater than our bound of error is indeed very small, indeed very less than and equals to our significance level alpha. Okay, standardize both sides, and then we can relate the critical value equals to bound of error divided by the standard error of P. Put this around, the bound of error is equals to the critical value multiplied to the square root of the estimated variance of proportion. Now in this textbook, it is slightly different with the formula for the sample size. Instead of just simply using the estimated variance, we want to use S, which is an estimated variance for the population. Okay, so S squared is equals to the true population proportion times 1 minus P and multiplied to n minus 1. Okay, this is the relationship between the true variance sigma square to the population's variance, estimated variance. Okay, so they are in the relations of the n to n minus 1. So let's put these into the formula, and then we can solve that. Let's this whole thing substitute into S or S squared. And then eventually we should be able to arrive at a simpler formula of our sample size. N equals or greater equals to N naught, our first assessment of sample size, divided by 1 plus N naught minus 1 divided by N. Okay, this is our target. So bound of errors, B squared equals to blah, blah, blah. So move around B or N to the left, B to the right, and play around with our fraction. Then we end up having N greater equals to this bit divided by this big thing. Okay, substitute this into S. This would be what happened. Okay, then it looks so ugly, but actually if you look at it clearly, as we find Z squared divided by B squared multiplied to P times 1 minus P. This less this bit equals to N naught. Or we can use our sample P if we don't have the population P, right? And then if we let this bit equals to N naught, put it back in here, N is indeed equals to N naught times N divided by N minus 1 divided by 1 plus N naught multiplied to N divided by N minus 1 divided by capital N. Okay, so it's not too bad. Then we solve the denominator, make it simpler, and then we find the relationship of the sample size should be greater or equals to N naught divided by 1 plus N naught minus 1 divided by population size. Okay, so let's look at the go back to the example 3.15, the proportion of unreasonable leave. The proportion that we estimate is about 8.8%. With 8.8%, conclusion is not good enough. So we want to say, what is the confidence interval of it? We did that previously, but now we want to say, if we want to conduct the survey again, we want to choose or determine the sample size so that a 99% confidence interval for P has a width no more than 10%. So what does it mean? It says that with the mean or with the width of our confidence interval of no more than 10%. So let's say if this is the distribution of our sample proportion, and this is our P, and the bound of error plus or minus, right? Both sides 99% of the time. So the width is 10%. So that means the bound of error, or on one side, the bound of error should be 5%. Okay, so at 99%, the critical value is 2.59. We can, using the formula that we derived on the previous slide, we can estimate the N naught equals to Z divided by B squared multiplied to our proportion estimate from the sample times 1 minus P. Okay, so we find the sample size should be 214. If we're not comfortable with that, we can correct with our denominator to find the real N. Okay, so we can see that the sample size, or N naught, is quite insignificant as compared to the population size. So after we correct that, it's still 213. Now, if we look at another questions, choose N to achieve 99% confidence for P with a width no more than 20% of P. So now it says we want it to be no more than 20% of P. So we want it to have a smaller width of P. So 20% of P with the width, so bound of error is 10% of P. P is only 8%, so 10% of it is 0.8%. So very, very narrow with the bound of error. So substitute again into the formula, we should find that N naught is about 6,899, substantially different from the previous requirement. Now correct for the population size. The actual sample size we need to collect is 5,789. Okay, so substituting the values into the formula is nothing complicated, but you need to explain why the sample size is significantly different between the N naught or the true N. In this case, why are they not quite different, etc. Okay. Estimate the difference between two population proportion. Okay, so this is quite straightforward. That's assuming the two population, they're independently distributed, then we can simply, similar to the Y bar case, we can simply subtract one proportion to the second proportion, and to see if this is significantly different from 0, then we can conclude that the two proportion, whether they are significantly different, right? So we can look at the estimated variance of P1 minus P2, which is if the population are independent, then we can add up the two estimated variance. All right, this example, change of opinion, verdict of 240 hours of social service on the pop star speeding. That happened in 2010. If you remember, if you're too young to remember what happened, was there was a pop star. He drove a speeding car on Garden Road, and he apparently he had a speeding, and then he was stopped by police, but he quickly swapped the seat with the passenger. And then the police find out that he was giving a verdict not to serve in a jail or anything, but he was giving 240 hours of social services. And then it roused a lot of media reporting that, saying that, oh, because of a pop star, that's why he's not going to jail, and etc., etc. I'm not putting any opinion on that, but a local newspaper has done a simple random sample of, and then asked some people whether you think this 240 hours of the social services is good enough, too heavy, or too lenient. And then on the first day of the verdict, we have some of the figures. 2 days after, more and more of the people talked about that, and then it aroused more people changed their mind, saying that, oh, this is too lenient, this 240 hours is not enough, and some people saying that, oh, this is quite heavy, etc. So we want to see if that 58% to 69% is significantly different. Okay. So given some of the data, the proportion difference, let's say using the first day, subtract to the 2 days after. So that is quite a very negative value. So how negative it is? Is it really significantly different from 0, right? So we find the variance of the difference of the two proportion. The estimated variance of the difference is 0.0325 square. We can find the 95 confidence interval for the changes of the proportions. So it is quite significantly different from 0. So we can say that this is quite a group of people has changed their mind after 2 days of the talking. Okay. Lastly, it says, in the first survey, are there any difference between the opinion on leniency and the adequacy? So the second question asks, within this survey, is there a significant difference between 58.1 to 26.2? Okay, but be careful, when we're trying to compare this proportion within the same group of people, then they are not two independent population or two independent sample, right? Because of the proportion depends on each other. So if that's the case, when we're trying to look at the difference and calculate the variance of the difference, for the variance of the differences, we need to sum up the variance of each of the distribution of the proportion and subtract the covariance of the proportion. Okay. Like we did the calculations or the proof earlier, the covariance equals to minus sigma square or PLPA divided by N. We can estimate the total variance. Okay. Again, this slide, I would say that I only test you on the difference of the Y bar or the proportion comparing to distribution when they are independently distributed. Okay, if they are dependent, then I'm not going to test you on that one because I don't need you to memorize the covariance formula for the dependence population differences. Okay, again, assignment 3 is out, so you can try to attempt some of the questions after listening to the first week of chapter 3. Next week, we're going to talk about the ratio estimation and the regression estimation under the simple random sampling. Okay, have a good weekend.